Good morning, Dave. Good afternoon.
Oh, good afternoon. Yes, good morning to you. Thanks for having me. Great to be
Well,
here.
Dave, it's good to see you again. It's been a short period of time. We were able to do one of the webinars during the week, and it's always a pleasure to see you. And at the same time, get a chance to get caught up on what's new in your world. And I mean, it's been, I don't know about for you, but the year of 2022 has been fast and furious in so many different ways.
It has flown by, and yeah, lots of changes, definitely. But definitely happy to be here, and humbled by the list of people I looked at who else was presenting today. And you know, I've got as much racing experience as most of them have in their fingernails, so hopefully I can make up with it a little bit with materials experience.
Well, I think what's interesting is a lot of the people that and organizations we've been talking to, I keep thinking about your company and how you bleed over into their racing fraternity, you might say, no matter what it is. And even the one I did recently about 12 o'clock today with the military, I think there's a lot of synergy right in that area that, you know, that they're looking for companies like yours to make our military better. So I look forward to your presentation and get a chance to, like I say, hear what you got to say when it comes to the state of Materion and what's going on.
Okay, yeah. Thank you. You know, guess I'm getting ready to start here. Let me see if I can figure out how to share my screen. Share screen, share that one. And then
it's coming. It was. There it is.
Okay, so let me, now you can see it, but how do I get rid of you and me? So, well, at least one of us. That's my last question here, is how do I make sure? Because
I tell you one way we can do it, because it's not important for me to be seen. I can fix me. Oh, the box still there. Sorry about that.
I did. Wait. There's me. How do I get? I got just you. I don't know. Anyway, you don't need to see me, I guess.
Run the slides and you'll be fine. Thank you.
All right. I'll do it. So so what we're going to talk about today, a little bit of a review from the last time, but you know, material solutions, as we say, so ways to use materials to solve those nagging problems and some examples of how that's been done. And when we talk about materials to solve nagging problems, it reminds me of a story. You know, the annual group of scientists get their big convention, which, you know, everybody knows that they have every year. Smartest brains in the world, of course, and they all meet. And they were talking and they said, you know, we probably figured everything out. I mean, we don't think we need God anymore, right? And I said, maybe not, but who's going to go tell them? Well, they all went and drew straws, and poor Myron picks the short straw. And he kind of goes up there and knocks on the door and said, hey, God, you know, we've been thinking about it, and, you know, we understand the Big Bang Theory. We go cloning. We can, you know, we can make our own power and everything. We're pretty much all set. So maybe you should, you know, just take it easy and go retire. And God said, well, you know, you have a point. You've come a long way, but I've been taking care of you for so long that I want to see if you could stand on your own 2 feet. So I'm going to challenge you to a man-making contest. If you can make a man as well as I can make a man, then I'm out of here. I'm going to retire. And Myron says, okay, you know, it's a deal. God reaches down, grabs a handful of dirt, says, I'm ready when you are. Myron reaches down to grab a handful, and God says, you get your own dirt. Well, hopefully we're going to find some things that are that kind of dirt in this webinar. And the bad thing about webinars like this is you can't tell whether anybody is laughing. But there's one. Thanks, Jeff.
I'll tell you what I'll do. I'll try to give the humorous side of it when it's appropriate. Okay, I'll grunt and I'll laugh and whatever else we need along the way.
Oh, all right. That is fantastic. Thank you. little bit of Ed McMahon, kind of. So
That's
sorry.
it. That's it.
Sorry. Okay. So when you think of the
And
company
Dave McQuinn
Materion-
said everyone's laughing, so we're good.
All right, that's good. So
Oh.
when you think about our company Materion, there's a couple of things that you should know about Materion. One, the materials we make are not easy to make. That's part of what we do. We started as a brushed beryllium company. I'll tell you about that a little bit in a minute. But beryllium is the first material we made. 1931 we were founded, right? And this company is based on materials that are difficult to work with, and the fact that they give a range of properties. It's not necessarily the strongest or the most conductive or the lowest friction. It's a combination of those properties. And that's where you can use those properties in engine applications. So very brief overview of the company. We've, as I said, we're founded in 1931. Anybody who knows Cleveland may know of Charles Brush the First, a competitor of Edison. There's a Brush High School here. His son isolated the element beryllium and had the company named after him after he had passed away in before 31. So we've been publicly traded since 72, about 1.3 billion, and largely the products you'll see today are manufactured in the US, but we have manufacturing locations throughout the world and sales locations as well. And when you think about Materion products, I mean, looking down the right-hand side, all of those places that we are, and you actually said, Jeff, military, that's also with the beryllium materials, a big area for us. We are near you or affecting you every day. So main landing gear bushings in aircraft, every bit of petroleum product you've got has come through exploration using Materion materials. The electronics in your computer, in your car. If you've got safety sprinklers overhead at work, there's a little beryllium nickel sprinkler or little beryllium nickel washer in every single one of them that has our material. So we're around, we're everywhere. And we've got that automotive that you see is largely electronics, but now that we're seeing the racing and series production automotive passenger cars going for more efficiency, longer life, that's where our materials come into play, the same reasons they do in other areas. So talking about the materials themselves, there are 4 materials that I'm going to talk about today. The first one is our Supremex. It's a metal matrix composite, 2000 series aluminum with 25% silicon carbide in a very fine dispersion. So it's a lot easier to machine than the MMCs that people are used to from a long time ago with big hunking particles that would break the tools. It was used previously before regged out in Formula One pistons. It is now, after some testing I'll show you, Cosworth chose it to put in the Gordon Murray T50, that 680 some horsepower, 12,000 RPM V12 as the material that could give them the lightest, stiffest, smallest piston. It's also used as valve spring retainers in MotoGP. And the property combination that you get from the material is that it is lightweight like aluminum, but the stiffness is more like a titanium stiffness, and it holds its strength better than aluminum does at high temperature. The silicon carbide gives it some wear resistance on the surface. The next material is a bronze called Performat. If you're in NASCAR, NHRA, a lot of other classes, it's well known there as a valve guide material. Our friends at Total Seal are also presenting today, have made it into piston rings. And the beauty of the material is it's got high strength. It's got steel sort of strengths. It holds its hardness and its strength to high temperatures. Got very low friction and thermal conductivity that is very good. So it's for getting the heat out, but still maintaining a strength. It's great for sealing things at high temperatures, which is a piston ring, a valve seat, a valve guide, of course. Our tough met material Tough Met 3 AT110. I mentioned landing gear bearings. Its main landing gear bearings in Boeing and Airbus. Every time the 737, the 787, or the A320 lands, there's a Tough Met bearing that it's landing on. High reliability, and also something I should mention. So when you buy these materials, they've all come from factories that have been audited by Boeing and Airbus. So the quality systems are first rate. They are used. Tough Met has been used in racing as things like small end bearings. It works as well as and sometimes better than the beryllium copper. It can be shims, washers, things like that, because of one of those things in the bottom, the property combination. It's got high strength and very low friction. It is non-galling. So it doesn't stick to steel, titanium itself, just about anything. And the other nice thing about it is its corrosion resistance. The picture of that bushing right there is one that I've had. I had that bushing for about 6 or 7 years before that picture was taken. So it's 77% copper, and that's as tarnished as it's gotten. And the last one I'd like to tell you about is the Alloy 10X, which is a copper beryllium, similar to the Alloy 3 copper beryllium that's widely used for exhaust valve seats, except with a little bit of zirconium, and it changes the properties significantly, especially at high temperature. These are used as nuclear generator rotor wedges. I'll tell you what they are, but they're nuclear generator. It's nuclear generator spec material, but it works fantastic for high temperature exhaust valve seats. It's got good strength, and it holds its strength at a high temperature. And for an alloy that can dissipate heat, there's nothing else like it at temperature. So as we're talking about these materials and going into the examples, there's a couple of things that I would like everyone to remember. One, first of all, most people know this. With all of the design software and help that we have, and all that we already know about creating engines and building things, the only remaining limits on design are the material properties. You could design anything, you just can't find the materials to make it work. So if you can have materials with a larger band of properties, or more of a combination of properties, it allows you to design more. It takes the limits off your designing. And the other thing is, looking at it from the other perspective, if you've got something you've designed and you can't, it's not working, it's so much easier to just find a material that works than to change the design. And you just think of it in terms of, I mean, there's a lot to go in with the testing and everything and changing the material, but just think of changing the dimensions on a print versus changing the name of the material. You change the name of the material, you cross it out, put the new material in, they make it the same, fits in. If you start changing the dimensions, then you've got to change the mating part dimensions, and you've got a tolerance to all these issues that come in. So just swapping out materials, a drop-in replacement, that's a lot of what we're going to be talking about today. So I've told you these materials are used in racing, told you that they're, told you they've got nice property combinations. I'll tell you a little bit, and then for those of you who've seen the EPAR Trade webinar that I think it was early fall that we did. This is a very high level overview of that, just to let you know that these materials are not only enabling design changes, but they also can last. And I'll give you a link to the EPAR. There'll be a link after this to the EPAR Trade webinar, as well as a white paper on the details of this testing. So Materion sponsored this testing at Cosworth in the UK, and they got a 2.0-liter EcoBoost i4 crate engine, brand new, and re-outfitted it with Materion materials and redesigned the parts around it. So the design changes they made in the cast or the pistons was a cast piston with a cast in ring groove insert. I put my cursor on it. You might be able to see there's a cast iron ring groove insert in there. And so by switching to Supremex, which is stiffer, still the same lightness, and doesn't need groove protection, they were able to reduce the piston mass by 20%, the pin mass by 16%, and by raising the ring groove closer to the crown. because you don't need that cast iron insert, and it's also stronger. The material is stronger at temperature, so you don't have to worry about it cracking or, you know, the ringland cracking. They moved the crevice volume, or the crevice, up. They reduced the crevice volume by nearly 60%. And when fuel gets into the crevice, it doesn't burn. So that should be an efficiency gain. The connecting rods, the connecting rod was a big change because of it was steel going to an aluminum product. You can see that it had to be made a little bit beefier, a little bit thicker to get the same stiffness. But at the same stiffness, it was 41% lighter than the original rod, and it had to be a little bit longer. As you see, the piston shorter to maintain the compression height. We had to make it longer. That does reduce some friction and some side loading, and it was piston guided. And the neat thing about that is Supremex runs really well on itself. So you had the Supremex rod running on a or guided by the Supremex piston directly, and the other components. There was a tough met bearing, small end bearing. I told you why. That's that works well there. It's also monolithic. There's no coating, so you don't have a disaster when you wear through the coating. And the valve seats and valve guides were the Performat alloy. Going back to that box at the bottom, the piston pin and rod, that's nearly 30% of the total weight of piston pins and rods. So you've taken out more than one cylinder's worth by reducing this weight. And the engine was not rebalanced and not recalibrated onto these materials, so it was out of balance and didn't take full advantage. We did see some friction gains, but the other thing was, hey, everybody knows a 41% lighter con rod would work. Will it last? So we asked Cosworth to put it through an OEM level durability test. And this is the test up here in the right hand upper right. So you idle for 15 minutes. Then there's about 12 minutes at maximum torque, wide open throttle. Then you get max power for roughly 12 minutes, and another a few minutes, not quite 5, of 90% power. All right, do that 40 times. So that results in 150 hours and 96 at wide open throttle, and absolutely no performance changes were seen related to the Materion parts. They blew the head gasket twice, so it shows you they were running the engine pretty strong. And there was no measurable wear on any of the parts. They expected that from knowing what they know about the pistons and the Performat for the seats and guides. The Tough Met, the rod was a surprise to them. Actually, no problems at all with it. And the valve seat recession was so minimal, it was a little bit of 1 to 2 microns of increase in valve lash. That was about it. So these are now materials that we tell you about. They'll last, they work, they're being used in racing. So if you keep these in mind, the idea behind this is having this in your toolbox. You're going to come up with this thing that if only the material would just do this. Think about these materials is where we're going with this. So there's the white paper. And the EPAR Trade webinar. And if you go back and watch this, you can copy those, or my email address is at the end. Send me an email. I'll be happy to send you any of this. So what we're going to talk about now is these drop-in solutions. And rather than going through each one of these, I tell you, these are some pretty neat things. Some of them applicable to what you're doing. Some of them may not, but hopefully you'll find them all interesting. So
hey, Dave,
yep.
real quick.
Yeah.
Before we move on away from the Cosworth test,
Yeah.
How much has anybody just speculated, including yourself or any of the engineers maybe you talked to? How much better do they think this test could have had results if they had taken the time to balance the engine from stem to from front to back? I mean, if they had gone through there and balanced every component to that engine, how much better? As good as it is, as great as it is, how much better do you think it could have been?
Well, we should have seen what we were looking for. We didn't see was huge reductions in fuel consumption, and by what we've read and studies we've seen, what we did should have resulted in 5 to 10% reductions. So that's a possibility. There's in the EPAR Trade the EPAR Trade webinar, I mentioned something about being able to take nearly a kilogram, I think 800 grams roughly off the crankshaft by rebalancing it. So all those kind of things added up, we're thinking 5 to 10% reduction in fuel consumption.
And the other thing is, it's like you almost did something that would have put more demand on your material because it's not balanced. I mean, you're actually kind of like beating on it in an indirect way, and trying to wear it down to a certain degree. And it didn't show that. I mean, it held up and it withstood it. Again, remarkable results across the board. That was something I didn't really get a chance. We didn't talk about the last time we did our seminar, but it just dawned on me. All of this, as great as it was, just straightforward numbers. Oh, by the way, it should have beaten it up a lot worse because it was nowhere near as smooth as it could have been.
Yeah. In fact, you can see the little bit of wear on the thrust side of the skirt. Just a little bit of burnishing of the skirt coating, and that's about it. Mm-hmm. So there was a lot of vibration, and boy, you could hear that thing when they were running it. That's for sure.
Yeah. Okay. Thank you.
All right. Thanks, Jim. So, okay. So go into these drop-in material solutions. One place that is a really difficult piston application, as everybody knows, is a two-stroke. Anybody who's run a relatively large snowmobile at wide open throttle for a long time knows that sometimes those pistons just don't last. And things can happen, like the crown can crack from excessive combustion pressure or detonation, either a fatigue or a single event. You get the pre-ignition event like down in the center there on the right side that just takes off the top ringland. Or something happens with skirt fatigue. You're slapping, you're running it too hard against the liner. So having a material that doesn't add weight and is stronger and holds its strength at temperature is a benefit here. And the material properties are hardness retention. So how much of that hardness stays after it gets hot or it's seen some high temperature. Also the fatigue strength at temperature. As something gets hotter, when you bend it back and forth or stress it repeatedly, it breaks a lot more quickly, right? And then there's the wear resistance. I was talking about the skirt coming in contact with things, and wear of the groove, things like that. So if you can increase the hardness retention, the fatigue strength, and the wear resistance in the material, that is a benefit. And to find all of that in something that also is lightweight and has good thermal conductivity, so Supremex is the drop-in replacement. You pay no weight penalty for it. It's and forged Supremex pistons have been put into tests that destroy other pistons and have had no problem at all. They're virtually indestructible in these kind of tests. So to talk about that, now you have to bear with me for a minute on this, because I thought I was going to be able to show you the piston I have in my hand here, but I don't think you can see that. So this is from the testing that we did at Cosworth. This is the change in hardness, or relative change in hardness of different parts. So this is going across the crown, 1, 2, and 3. Then in the pin bore OD, so the outsides of the pin bore in 2 spots on either side. Then up the skirt through 10, and 11, 12, and 13 were each of the top 3 ringlands. And what you can see, the Supremex is usually in that 225, 230 Vickers range. And it lost some on the crown. I mean, they were running it hard, right? And this is only the base running. This wasn't through the 150-hour durability test that the cast piston lost this much hardness. But there's still a gap maintained between the two, right? And also on the ringland, it's still harder. The reason the ringland up here doesn't appear to have softened is because it's got that cast iron reinforcement piece in there. But in general, across the board, during this 150 hours of testing, this Supremex piston retained its hardness, and the folks who have tested these pistons in in dynos on two-stroke dynos have said the same thing. It's incredible how much hardness is retained after they put it through a wide open throttle test. The other thing to look at is fatigue strength. So this is rotating beam fatigue. You've got a rod that's spinning and you're just pulling the rod downward as it spins. So that is fully reversing, so the rod is bending in essentially by rotating, bending in all three direct or in a circle. So it is fully reversible fatigue. And what this is on the left is the stress applied, and that's, sorry for switching units on you. These are MPAs now, but the stress applied at where it breaks at that temperature at 10 million cycles, right? So you've got Supremex is the blue, 4632 is the brown, and the gray is the 2618. And then each of these are the temperatures in degrees C. So there's room temperature all the way up to 400. And as you can see, the Supremex maintains a gap between the two and maintains an advantage. And we didn't even bother testing these two materials out at 400 because they just don't do very well. So there's the fatigue that's going to help if you have thermal fatigue from overloading the crown or skirt fatigue, as we were talking about. That's the property that's going to help at the temperature. And the last thing is, again, with the skirt, if you're wearing that or wearing some other part of the piston, you can thin it out a little bit. Looking at wear resistance. So this is a pin on disc sliding back and forth. There's a 4340 steel pin on either in the brown, a Supremex disc, or blue is a 2618 disc. And you can see there's an appreciable factor of 4, even higher. When it gets really high, the mass loss is a lot in the 2618. And actually, the reason it comes down here as we go to a higher pressure is because you're actually deforming the material and not scraping it off. So it's not losing mass. It's just moving out of the way. But again, this is the wear resistance that's provided by that silicon carbide, those silicon carbide particles that sit on the surface and hold, hold against the weight. They're very low in friction as well. So now thinking about that, and remember we said that the groove wasn't protected in a Supremex. You don't need to protect the groove. Well, in forged or cast pistons, because that piston we replaced was cast, and some of the two-stroke pistons are cast hypereutectics. Do you need to protect the groove in those? And groove damage can come by low speed pre-ignition, and that's why all of our cars have, or most of our cars, depends on whether you tune yours or not, but most of the OEM cars have that groove insert in there. You can have knocking there. You can also have surface fatigue from the ring sliding back and forth if you get some friction there, right? So what can you do on a forged piston? Everybody knows anodizing is a pain in the neck. Trying to get a narrow, deep groove like that anodized is really tough. Putting a coating down there isn't easy either. But if you don't, you've got a very limited life with a 4032 or a 2618 or even the cast hypereutectic. For the cast pistons, you can put in the ring groove insert, right? But there's a penalty that comes with that. It's heavy and it doesn't conduct heat very well, right? So one of the things we came up with is the Supremex groove insert. We've already proven the groove durability. It works in that durability test at Cosworth. It's worked in other durability tests. And we did do a proof of concept on it that I'll show you next. So when our head of technology in our factory in Farnborough, England, that makes the MMCs said, well, yeah, you can cast aluminum around aluminum-based Supremex. I said, wait a minute, it won't melt? No, it's because that ceramic reinforcement, he called it the ceramic skeleton, holds everything together. And if you do it quickly enough, it doesn't change the properties of the Supremex. So what you see up here in the right is there's a little ring of Supremex. This is a round puck that we made. It was a gravity fed mold, right? And we just poured in aluminum around the Supremex, and boom, it worked. Now, you can see this is the first casting trial. You can see a little porosity at the interface, but if you do what they do with, with the cast iron rings and dunk it into molten aluminum first, and then put it into the die casting mold, which shoots in very quickly, you've got a very good bond there. So you've got that great wear resistance. The CTE match is better too. So the steel won't expand as fast as the aluminum. So naturally, if you get a piston with a cast insert in there and it gets hot, that aluminum is going to want to pull away from the steel that is not expanding as fast as it. So Supremex is closer to aluminum. It's going to expand and take up that gap more. If you're worried about getting heat out through the top ring, which is one of the main conduction paths to the liner and to the coolant, right? Having cast iron in there is about a quarter of the conductivity of Supremex, right? And you've taken about 20 grams out, because that's what one of those rings, one of those cast iron rings makes. It's back to being the density of aluminum. So it's a great opportunity, and we have some people working on that with now with cast hypereutectic pistons basically for two-stroke engines. So next thing we're going to talk about, moving to the next application, is replacing needle roller bearings. Right, a needle roller bearing is they're nice. They provide some low friction. They get a tight fit, and they're a pain to put together. They vibrate a little bit, and they're big. But what can happen to them, what can go wrong, is you can get flat spots if you overload it in a stationary condition. You get flat spots on the rollers. That's called Brunelling. The cages can twist. You've seen, I'm sure people have seen that, where you have the cage twist and needles are all over your engine. That's not a good thing to have happen. And impact failures. Again, you could blow the cages apart with an impact. And if for some reason your filters aren't doing the job, or you're in a dirty environment, lubrication contamination is bad for those small little spaces in the needle roller. So what if you could just change that to a plain sleeve bearing? Saves some space and takes away a whole lot of the failure modes, right? Needs to be something that's low friction, needs to be something that's very durable. But going from a needle roller bearing is going from the automated serviette, it's like going from the automated serviette to a napkin. It's just easier, it's cheaper, it's simpler, and it works better in a lot of cases. So to get to the application in racing, I got to tell you about the first time we did this. Was in a pneumatic torque wrench by a company called Torque Up. And Torque Up makes these very strong pneumatic, very high torque pneumatic torque wrenches. The last one they were making was this Raptor. It is the Raptor 6,000 foot-pound Raptor, actually. So 8,100 Newton meters. And they were using needle rollers in the planetary gear bearings. And the needle rollers were actually at the high torque twisting and coming apart. So by switching to Tough Met, they not only made it more durable, right? They didn't get any increase in friction noticeable. They increased the load capacity. And the other thing that happened was they actually decreased their assembly cost, because the workers, rather than assembling needle rollers one at a time, were just popping these bushings in, right? And that allowed the launch of the Raptor. This is a page from an old calendar we had at Materion, so we're thankful to the people at Torque Up for letting us use this. But about that time, some people at Skunk 2, and this was published actually in Race Engine Technology, which is why I'm saying Skunk 2, but they needed cam follower bushings, and they were having some needed cam follower bearings, and they were having some problems. They take out the VTEC and just run the a double lifter like this, or a double rocker arm on the big lobe, right? And it generates a lot of power, but it also generates a lot of pressure on that follower roller. So when they couldn't find a needle roller that was specified at high enough at these high PVs, 620,000 PSI surface feet per minute it's high. And when they put in Tough Met, they were able to downsize the roller because it had a smaller areas that gave them less inertia, and it met the durability requirements. Never had one fail. So in thinking of going from roller bearings and gearbox bearings to something else, another thing, as we're talking about hybridization in some of the talks today, would be e-axles, right? Or think about this, any high power density, high speed gearbox that you would have. Could be in a transmission, could be a differential. But this particularly, this related to e-axles, we, you know, if you look at an e-axle, it's putting the electric motor, the gear reducer, and the inverter all in one small package, make this package as small as possible. So that gives you good efficiency when it's all together. You put them in line if you've got a planetary gearbox. That efficiency gives you longer range because it's a small package. If you've got a front wheel drive car, you can just bolt it on the back wheel and you've got a hybrid right there. And to make it as small as possible, you get the space savings. But you've got a problem now. You put a lot of electrically generated heat, a lot of resistive heating, plus a lot of frictional heating from the gearbox into a small package that doesn't have a lot of chance for lubrication, and definitely doesn't have a radiator on it, right? And the other thing is noise and vibration. You want to keep the noise and vibration down. That's why some people are using needle rollers, but if you can get rid of them for this, you'd reduce the noise and vibration. And for something like that Lexus, that's an important thing. You reduce the cabin noise. So here's a gearbox. I cannot find, and I'm sorry, I cannot find a gearbox picture that isn't somebody. So this is GKN's. GKN, what is behind that sign that I can't get to go away? There it is. They don't use or endorse Performat. I just wanted to credit them for a nice little picture there, but you can see the inline, you can see the inline planetary gearbox. And as you're getting the smallest package, trying not to have needle rollers in there because of the space, because of the vibration, it can overheat. And that lubricant can break down. And what happens then is that if the lubricant breaks down, it either gets really noisy with needle rollers, or if there are other bushings, and if there are bushings in there, it tends to seize, right? Seize to the shaft. Everything kind of swells. There's no lubrication. It seizes. So a solution to that is Performat. We have found out that Performat performs at low pressures and high speeds, performs as well or better than ToughMet as a roller bearing or a gear bearing like this. It has the high strength and hardness that gives you the durability. Performat has a similar coefficient of friction under these conditions, but it's got 4 times the thermal conductivity. So when you start to get things hot at the center of that gear, it could dissipate the heat and pull it away, right? And it is working in a couple applications now. The properties to look at, okay, if you look at a typical aluminum bronze that is used for these applications, used for planetary gear bearings, compared that to ToughMet, but actually more so to Performat, you've got a lot more hardness for the durability. The thermal conductivity is a factor of 4, even more than 4 over ToughMet. And believe it or not, the coefficient of friction and the wear rate is lower than with ToughMet. So this is a solution for any, Performat is a solution for any gearbox where you can't run it as fast or as high as you want, or make it as small as you would like. So, and of course, we have gobs of data on the testing, but at least you can see the Performat, which is the red triangles, has a wear rate in our block on ring testing that is 1/10 to 100th that of the aluminum bronze, and very, very similar to the best Templar ToughMet we have, the TS95. All right, so keep switching gears here, but that's okay because
real quick, Dave, I've got a I guess you call it, I'm gonna ask a big dummy question. Difference between or clarification between a bearing and a bushing.
Oh, yeah, good point. Okay, I should be, it's a lot of words. Bearing is anything that, it takes rotation. It can be a thrust bearing or a journal bearing, anything that has a rotating for these purposes is
Okay.
rotates around a shaft or has a shaft rotating inside it. A bushing is a sleeve bearing or a plain bearing. It doesn't have rolling elements. So I'm probably getting sloppy and using them interchangeably.
Well, I just, again, just paying, watching and saying everything that you're saying here, I'm getting, blown away with the ability to be able to take what appears to be a solid bushing and put it into a roller bearing position and have the same effectiveness, if not better results than you can with the previous. And, it's just, once again, I think it speaks very highly of the people and folks at Materion, how they've been able to come up with enough. I mean, it's like the mad scientists, they're able to make, take a little bit of this, a little bit of that, and they get it mixed together. And all of a sudden we're able to accomplish all the above and not generate more heat in the process. I mean, which I think is phenomenal.
Yeah, it is really, I mean, full disclosure, one of the places where you have to be a little bit careful about replacing rolling element bearings is if alignment isn't good, because roller bearings tend to be self-aligning or enforce some alignment on the system. And so if there is misalignment, it's not a great place for to switch to a plain sleeve bearing. But then again, misalignment in engines causes all kinds of other problems. So we usually don't have a lot of that issue in these applications. So
carry on. Like I said, it was just kind of, I wanted to ask that question for my better understanding of what I'm watching here.
No, yeah, I appreciate that. Go ahead and interrupt me anytime. That's fine.
Well, thank you.
Yeah. So now getting a little more ethereal, if you will, because I had ethereal in the topic here. What about, we're seeing a lot of interest in hydrogen ICEs, not fuel cells, but rather hydrogen ICEs. And, there's a lot of investment in it, right? And if you can make it actually tank the tailpipe, it's carbon neutral. And if you can make green hydrogen, it's even more carbon, but it's not going to, generate CO2 out the tailpipe. It uses an existing engine architecture that we all know and love, right? And that's one of the things I've heard that may be a way if there's pressure on racing in the future about carbon neutrality. Hydrogen's one of the options to keep that roar going and only putting water out the tailpipe. I hope it never comes to that, but it's as you see, because it's a good solution for long haul transportation and for power generation, because you can store a lot more power density in hydrogen than you can in a battery, for example. OEMs are using their technology platforms, which is their race teams, to do this, just like the Toyota Gazoo made that Yaris that you can read about there that runs very well. And you can see that the Yamaha motor president says, hey, motors in our name, we want to keep these things going. So the problem you have with the hydrogen is that it interacts with the metals differently, right? So it diffuses and embrittles things like steels. It can when hydrogen gets into a steel, it can make it very brittle and cause cracking. And copper alloys generally don't do that, but it's an awfully good thing to check. And if you can find a copper alloy that's as strong as a steel, well, you might have a substitution replacement. One of the things I didn't know is there's some concern about hydrogen, or I didn't know, a year ago, is there's some concern about hydrogen removing the native oxide on stainless steel. It can reduce the oxide on stainless steel in a certain environments, and then cause the stainless steel to corrode. So if you think I got a corrosion problem, I'm put stainless steel in there. Not only are you sacrificing conductivity and tribology, friction and wear, but you might not get that corrosion resistance. And the other thing is, hydrogen doesn't lubricate like diesel or gasoline does. I mean, you may as well, put an extra hydrogen in doesn't make it any more slippery. So needing to find something that is lower in friction. And we know that Performance low in friction, it doesn't have corrosion issues because it doesn't have, and hydrogen because it doesn't have the native oxide. But then what does it do in hydrogen? And we took a look, went to a couple of very august universities in Germany and did tests like you see over there on the right, and found out that, we know from our oil and gas experience that copper beryllium doesn't absorb a lot of hydrogen, doesn't have hydrogen embrittlement issues. Performant absorbs a fraction of that even. And like whatever that is, an eighth of what steel absorbs. And then without the cathodic charging, without forcing the hydrogen into the sample, just nothing gets in. So you've got now a material for hydrogen that you can use for valve seats, valve guides, piston rings, and not have to worry about the hydrogen exposure of this material. So if it comes to that, or if you're working on them, it's definitely a material to look at for sealing components. And then going one more ethereal, let's talk about nuclear generators. So alloy 10X is the ultimate valve seat alloy. It's similar to the alloy 3, which has been traditionally used forever in exhaust valve seats. It's the redder of the two copper berylliums. And we have this alloy 10X because it works where alloy 3 can't. It's developed for nuclear generator rotor wedges. And rotor wedges go in these slots that you see on this big Siemens rotor wedge. And this thing is, I think it's like 6 feet in diameter and 30 feet long, and it spins at 3,000 RPM. And the rotor wedges keep the windings from flying out, which can cause all kinds of bad things to happen and pieces of metal to fly everywhere. So the rotor wedges have to be durable. And there's a condition, at least at one point in the design of these, where there might be enough current through the rotor wedge to hit 800 degrees Fahrenheit. So it had to hold the strength at 800 Fahrenheit, right? And it had a ductility, a minimum ductility requirement, a minimum strength requirement, also with the thermal conductivity, and in this case, electrical conductivity, which are related, So what happens in all copper alloys is, or precipitation hardened copper alloys like these, is as you get close to something called the recrystallization temperature, and that's a whole metallurgical class I don't think I could ever even give, but as you get closer to that, the ductility goes down. You would think as you heat it up, it gets wobblier and softer. Well, it actually gets more brittle for a start and then goes through a transition. So if you put in a little bit of zirconium, you raise that recrystallization temperature to a higher and allow the metal to be used at a higher temperature. And so a while back, someone with a stock car was using alloy 3 and had fatigue cracking, heat checking. You could actually see like cracked check marks on the surface. And they were running it as hot as they possibly could, but the alloy 3 wasn't holding up. We'd never thought of it before, but it was, you got anything else that might work? And so we actually grabbed a hunk of rotor wedge bar and they machined some exhaust seats out of it, and the problem just went away. And a few users are using it now, and several other classes have adopted it. I haven't seen a lot of the cracking issue, but it also helps because of retaining its strength. It helps to avoid valve seat recession. And there is nothing with this kind of conductivity, and you need thermal conductivity in the exhaust valve seats to get the heat out of things like the exhaust valve bridge, right, to distribute the heat, get it out of the head of the valve. Nothing with this kind of ductility has that elevated temperature property set. And just to give you a little bit of overview on that, here are the yield strength, don't have to worry about the values, and the ductility is on the right, elongation's on the right, in tensile testing of Performat at the top, alloy 3 and alloy 10X. And what you see happening here, and I've got other graphs that would actually show it better if we ran out here, but the Alloy 10X holds the strength better and also doesn't embrittle. This is Alloy 10X up here. Doesn't embrittle. There's the ductility minimum and it's going back up. But everything else is getting really, really brittle down here. Doesn't stretch much before it breaks. 10X gives you another 100 or so degrees. So that's why it's used in these applications, and we haven't heard a durability question about it at all. The only thing we've heard a couple of times is, hey, you got anything better than that? And I think we'd have to get our own dirt. Anyway, so a little bit quickly, you can go back and get these. I know there's no time to get links, but they're in this just in case. Anybody who wants to learn more about our materials, feel free to call me. There is also our technical assistance, or if you go onto our website, you see a little talk to an engineer box. You'll actually get an engineer who's worked many years in the plant, who has access to a database that has all of our material properties. They're pretty darn good at that stuff. So if you got questions, me or them, our international sales offices are there, and there's a couple of white papers on engine testing. A couple other things I'd like to say before the end of this is, it's not easy being an individual and trying to buy metal from a mill. We like to sell lots of stuff and tons, and if somebody needs 3 feet to make a couple of bearings, well, that's why we partnered with a couple of distributors who are really good at doing that. Going to stock our materials, and they are stocking our materials. So there's Edro in the US. Edro has been a long-time distributor to the plastic mold industry for us. They do a great job, fantastic to work with. They will be at PRI this year, and Materion will be supporting them in booth 507. And for those of you in the UK and Europe, Smith's High Performance, which you probably all know, is stocking right now as well. Again, wonderful people to do business with. And they should have, they're stocking now. They should have everything that you've seen available in first quarter of next year. So that's where you get it. And there's my email address. So hopefully that was rapid fire, a lot of stuff, but hopefully
it was, Mr. Cruz.
Yeah.
But at the same time, you talk about your company, everything's coming at you fast and furious. And I talked about them being mad scientists. Well, you're the math professor that goes right along with it, because you did an excellent job. I loved your presentation, just like I did earlier this year. I learned a lot, and you guys have made, once again, it's a heck of a presentation in a short period of time, and a lot of things are happening with your organization and Materion across the board and around the world. And Francis, I think they do a pretty darn good job. What do you think?
They absolutely do. Thank you very much, Dave.
Registering on EPAR Trade is easy. To start, click on the Join for Free button on the homepage. First, search your company to see if it's already in our database. If you see your company on the list, click on it to select it. Then, choose Claim Company if you are one of the decision makers, an owner, marketing person, or main company contact. Or choose Join Company if you are an employee, and press Continue. If you couldn't find your company in our database, select Register a New Company. On the following page, fill out your name, email, phone number, job title, and choose a secure password. If you chose Register a New Company, you'll need to choose your business type. Select Supplier if you're looking to display products or services and connect with buyers. Choose Racing Business if you're looking to source new parts and connect with suppliers. Choose Race Team if you own or are a member of a professional race team. Then, enter your company name. Please provide a website, Facebook page, or LinkedIn if you have one, and choose to either claim or join the company. You can view and agree to our terms of use here. If you'd like to receive our weekly newsletter, choose Accept. Finally, click Register Now and your registration will be submitted for approval. An email will be sent to your inbox. Please confirm your email address and you will be approved shortly. Welcome to EPAR Trade.